Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 1.4, day 1, entitled Rational Expressions. And today we're going to talk about the first two objectives. We're going to talk about the domain of an algebraic expression, and then we're also going to talk about simplifying rational expressions. And first thing we have to talk about is what a rational expression is. When you just divide two algebraic expressions, it's called a fractional expression. So that's just like the examples here. You have 2x over x minus 1. That's a simplified fractional expression. On the second one, square root of x plus 3, and then x plus 1 is the denominator. That's as simplified as it can get. It's just an expression. Even in this last one, this x squared plus 4, it's a sum of two squares, so we can't simplify that anymore. So that, again, is just another fractional expression. But a rational expression is what we're going to be simplifying today. And this is where the numerator and the denominator are polynomials. And we want to ideally be able to factor so that we can simplify them down further. Now this first one here, 2x over x minus 1, it's the same as the one up above. But again, it's a monomial over binomial. It's as simplified as it can get, so it's still a rational expression. The second one in the denominator, we have an x squared plus 1 again, so it's a monomial over a binomial. It's as simplified as it can get. X squared plus 1 is a sum of two squares, not a difference of two squares, so we can't break that down anymore. And then we have x to the third minus x, and then x squared minus 5x plus 6 as our denominator. So there we have a binomial over trinomial. So that's going to be the more complicated looking type of expressions that we're going to see and have to simplify. Now, the next thing we have to talk about before we actually start simplifying an algebraic expression is what the domain is. And the domain is, or the domain of an algebraic expression, is the set of the real numbers that the variable is permitted to have. So there's the definition right there. And so this just ensures that basically the denominator of a fractional expression can't be undefined. So if you look over in this little box will be in your book as well. It gives you some examples. If you have 1 over x, your domain is all the x values that are not equal to 0, because you can't have 0 in the denominator. If you have the square root of x, you can have pretty much any number for x except a negative 1. So it has to be greater than or equal to 0. And then also for 1 over the square root of x, we can't have the denominator being 0. So again, it has to be greater than or equal to 0. So let's take a look at these first examples here. And all we're going to do is find the domain. So you're going to see problems like this in your homework as well, just finding the domain. And this is a concept we're going to use all throughout the year. So you want to get really comfortable with this. And actually in part A, we have no denominator. So we don't have to worry about the domain having any type of restrictions. So our domain is going to be all real numbers. So that's pretty straightforward, pretty easy. For part B and part C though, we do have denominators in our expressions. So we are going to have to make sure that our denominator cannot be equal to 0. Now for part B, in order to do that, we want to factor our denominator. So we're going to factor by guess and check. So we would need the factors of 6, that would add up to a negative 5. Factors of 6 that'll get me to a 5 are a 3 and a 2. And to add up to a negative 5, I need them both to be negative. And then the negative 3 and the negative 2 will also multiply to a positive 6. So that is really the factored form of my denominator. And doing that helps me recognize what values the denominator can't be. Because if I had x equal to 3, if that was the value of my x, that would make this expression here, the x minus 3, that would become 3 minus 3, which would be 0, times this term, whatever it is, would make the whole denominator 0. So I can't have a value of x equals 3. And same thing over here. If I had x equals 2 for a value, That would make the x minus 2, which would be a 2 minus 2, that would make the whole expression 0, times whatever's in the first parentheses, doesn't matter. 0 times anything is 0, so that would make my whole denominator 0. So my domain for this problem is going to be any number except for 3 and 2. And the way we write that is in our set notation. All of the values of x such that x is not equal to 2 and x is not equal to 3. Now you can write out the word and for me, that's fine. If you want to do the little upside down U for intersection, that is fine as well. That's how the book will write it. Now for part C, we have to take both the numerator and the denominator into account here because in our numerator we have a radical. So for our numerator, we have to have everything that is greater than or equal to 0. Because we can't take the square root of a negative number. And for my denominator, it's already as simplified as it can get, but I can't have a value that'll give me a denominator of 0, so I can't have my x value being 5. So those are my two conditions there. And again, I'm going to write that in set notation. So all of the x values such that x is greater than or equal to 0 and x is not equal to 5. Just remember that when you have a radical in the numerator, you have to take that, any limits on that radical into account as well as what's in the denominator. Now to simplify rational expressions, we really just have to factor first so that we can cancel anything that's alike from the numerator to the denominator. Now you've done this, you've done simplifying rational expressions, like if you have 10 over 15, you know that to reduce that, you divide them both by 5, so you end up with 2 over 3. And we're essentially doing that as well, except instead of dividing by a constant, we're going to divide by a monomial or a binomial or even a trinomial. So your examples will look like this. Here we have x squared minus 1 over x squared plus x minus 2. So in our numerator, we have a binomial, and in our denominator, we have a trinomial. Now in my numerator, I can't take out any greatest common factors. Remember, that's what we always want to try and look for first when we're factoring. I'm going to put a little note here that we need to factor. And then we need to cancel. Those are the steps that we're following. So I can't take a GCF out of the numerator, but in my numerator, I do have a difference of 2 squares, so I can factor that. So I'll have the x and the x, and then a plus 1 and a minus 1. Remember, for a difference of 2 squares, you want the factors of 1 in this case. Factors of 1 are 1 and 1, and then you need one set of parentheses to have a plus and one to have a minus. That's the pattern for difference of 2 squares when you factor it. And then in my denominator, again, I don't have any greatest common factor that I can factor out, but I do have a trinomial, so that means I have to try and do guess and check. So I'm going to set up my two parentheses. Factors of x squared are going to be x and x. And then I need the factors of 2 that are going to get me to a 1. So the factors of 2 are 2 and 1. And to get those values to add to a positive 1, I need a positive 2 and a minus 1. So that way, if I checked my outers, I would get a negative 1x. Inners would get me a 2x. Those would add up to the 1x that I had there in the middle. And then if I multiplied the 2 and the negative 1, that would multiply to the negative 2 that I had at the end of my trinomial. Okay, so I did the correct factoring for both of those. Now, when you look at this expression, now that we have multiplication, now we can divide the top and the bottom by the same thing. So we're going to cancel. Okay, so that cancellation step, that's kind of like doing division. And I'm going to cancel out the x minus 1 and the x minus 1. So I can only do that when the stuff in the parentheses is exactly the same. Okay, I have to have multiplication in order to do that. So my final answer then will be x plus 1 over x plus 2. Now, a common mistake that students make is that they don't do the factorization first. They don't turn the addition and subtraction into multiplication. You can only cancel when you have multiplication. Really, you have 2 times 5 over 3 times 5. That's what allows us to do this dividing by 5 here, is because we can really write 10 and 15 as multiplication. And we can divide out that 5. We can cancel out those multiplications that are the same. But a lot of times when students see problems like this, they want to take the x squared minus 1 and the x squared plus 1x minus 2, and they say, oh, there's an x squared and an x squared, and they cancel those off. Or they say, oh, 1 minus 2, that's a 1. And they keep doing all kinds of illegal cancelization. So that is what not to do. You have to factor first before you can cancel out any like factors. So there are your practice problems for this evening. Good luck, do well, and stop by and see me before school if you have any questions.